Hi, let us proceed with our discussions about the design of reinforced concrete pad footing subjected to only axial loads. So far, we have done the calculations to determine the nominal cover, determine the size of the pad footing, check the soil bearing pressure not exceeding the soil bearing capacity, and then calculate the ultimate soil pressure in order to determine the moment acting on the column face, and then design for the reinforcement. Based on the calculated AS required, we propose sufficient amount of reinforcement bar so that the AS provided is greater than the AS required. This AS provided is later to be checked against the serviceability requirements, such as the AS minimum as well as the AS maximum. The proposed amount of reinforcement bar include 12 units of H20 mm diameter bar in both the major axis and the minor axis. Having this confirmed, our next step will be checking for the shear resistance. In terms of the shear resistance, there are three types that we need to check. First, it will be the shear resistance at the shear plane of 1D from the column face. Second, we will need to check the shear resistance on the plane of 2D from the column face. And lastly, we are checking the punching shear resistance at the perimeter of the column. We will need to make sure all the shear resistance pass so that the pad footing can be used. First, let us look at the shear resistance at 1D from the column face. We need to first determine the VED, which is the shear loads taken by the shear plane here. To calculate this, we need to first determine the locations of the shear plane, which is located at 1D from the face of the column. The D for the major and the minor axis we have calculated previously, which are 444 and 432 mm for the major and the minor axis respectively. And then we need the bearing pressure due to the soil. This we also calculated previously from the equations to determine the ultimate soil pressure. Since the pad footing is only subjected to the axial load without any moment, that means the soil pressure is going to be uniform throughout the contact surface area. It was calculated that the soil bearing pressure will be 250 kN per meter square for both the major and the minor axis. Now we need to determine the shear loads acting on plane 1D from the column face. Knowing the locations of this shear plane, we will need to get this area multiplied with the soil pressure. This will give us the VED. In order to get this shear area, you will need to first get this distance. This can be done if you sketch the diagram. First, know the dimensions of your pad footing, which is 2 meters times 2 meters. And then the dimensions of your column, which is 300 times 150. Your column, it will be at the center of the pad footing. 2 meters here minus 300 divided by 2, you get your Z1. This is how you get this at 50. Minus the effective depth D, which is 444. That will give you this distance equals to 406. Having the stress uniform here, find the area here to determine the shear force per unit plane, which is you use this 250 times the distance, which is 406 mm. You get 101.5 kilonewton per unit width. This represents the shear force in a plane. Multiply the width here, which is 2 meter BF. You get the shear force equals to 203 kilonewton. This will be the shear force taken by this plane. As for the minor axis, we are looking at this plane, and the respective area it will be here. Multiply the uniform stress, you get your VED. Since the columns is not square, this going to alter the Z or the Y. Eventually it give you another width here for you to determine the shear force. Imagine you look from this side, your pad footings width, which is 2000 mm, minus the column width, which is 150. You get this distance and this distance in total, divided by 2, assuming the column is placed at the center. You get the Y1 equals to 925 mm, minus the 1D effective depth from the column face, which is 432 mm. You get the distance here from the shear plane equals to 493 mm. And then the soil pressure is uniform. 250 times this width, which is 493 mm. You get the shear force of 123.3 in a plane. Multiply the width here, which is 2 meters. You get your shear force equals to 246.6 kilonewton. What you see here, the shear force on the plane differ, even though we are using the square footing. The reason being here is due to the rectangular sections of the column. The smaller width in the minor axis leads to you more rooms from the column surface to the edge of the footing, minus the effective depth. That will give you a greater distance from the edge to the shear plane. This greater distance will give you a larger areas contributing to the shear force. That's why you will get a greater shear loads in the minor axis. If you find yourself difficulty in identifying the more critical site, you can always do the calculations for both axes. Then you're going to check the shear resistance in the both axes to confirm if the shear resistance is sufficient. Let us proceed with the calculations. Now that we have obtained the shear force, this shear force is later to be compared with the shear resistance. The shear resistance will need to be greater than the shear force to prevent the shear failure at the plane of 1D from the column face. To determine the shear resistance, there are two equations. We have VRDC and also VRDC minimum. VRDC means the shear resistance of the concrete, taking into the considerations of the reinforcement embedded in the pad footing. As for the VRDC min, it considers the shear resistance of the concrete only. We will need to choose a bigger value of the two as the shear resistance of the pad footing. In order to calculate that, we will need to first determine the factor K. which is in the functions of the effective depth and not to be exceeding 2.0. So we will calculate the factor K here. The effective depth for the major and the minor axis is here. Substitute into the equations. You get the K value equals to 1.67 and 1.68. The calculated value is less than 2.0. Therefore, we will use the exact number 1.67 and 1.68. Next, we need to determine the reinforcement ratio, which is rho 1. This rho 1 here is depending on the AS, which is the longitudinal reinforcement bar provided in the pad footing, divided by the effective areas, the width times the effective depth, quantifying the percentage of the reinforcement bar out of the effective areas. And this ratio here will need to be less than 0.02. That means not exceeding 2% of the effective area. While computing this number, you have to be careful. Careful with the amount of reinforcement bar used, especially when the AS provided in the major and in the minor axis differ. Also, this AS1 here refers to the actual reinforcement bar provided. You should use AS provided instead of AS required. As for the B and D here, you will have to look into the effective shear plane. Now let us look into the calculations. The AS here, it will be the AS provided. We calculate for the major axis. The AS provided in the major axis is 1357 mm square, divided by B and D. We have no issue with the D here, because the effective depth in the major axis is 444 mm. As for the B here, you will need to look at the arrangement of the reinforcement. Let's say we are talking about this pad footing. The reinforcement bar in the major axis will arrange in these orientations. The reinforcement bar shall pass through the shear plane here, and this reinforcement bar will act as resistance together with the concrete at this plane. Because of that, the B here shall refers to this width instead of this. Why is it so? Because these are the reinforcement bar passing through the plane, but this reinforcement bar contribute no resistance to this shear plane. Therefore, while quantifying the effective area of that particular shear plane, we are talking about this width times the effective depth, this plane. Now, how much is this width? It is equals to 2000 mm. Substitute the value, you get 0.00153. The number is less than 0.02. Therefore, you will use the number calculated. If the numbers go beyond 0.02, you will use 0.02 here. Then you calculate the reinforcement bar ratio for the minor axis. This time, your AS, it will be the reinforcement bar arranged in these directions, where the reinforcement bar in the minor axis, it will be the same as the bar in the major axis. Use this as provided, divided by the effective area in this plane. You are talking about this width times the effective depth, since you are talking about this reinforcement bar that passing through this shear plane. So this width here, it will be equals to 2000 mm, and the effective depth is equals to 432. That gives you your rho 1 equals to 0.00157. The number is less than 0.02. Then we will use it as the rho 1. Having the K and the rho 1 calculated, now you may determine the VRDC. Substitute the K into the equations and the rho 1 into the equation. The FCK, it will be 30 Newton per mm square. The width here, it will be depending on which plane that you are referring to, either the major or the minor axis. Since you are doing with the square footing, so the width for both major and the minor axis, it will be the same, which is 2 meters. And then the effective depth, as calculated earlier on, 444 and 432. Substitute into the value, you get these two. VRDC in the major axis and VRDC in the minor axis. Next, we use these equations to determine the VRDC minimum. Substitute the value K into the equations for both major and the minor axis. FCK equals to 30, B equals to 2 meters, and D, it will be due to the major and the minor axis, which are 444 and 432. Then you get 360 something. Now to determine your shear resistance, it will be the bigger value of the two. Compare these two numbers. The bigger value, it will be the shear resistance of the shear plane. Same goes to the minor axis. This shear resistance is later to be compared with the shear loads that we have calculated on the shear plane, located at a distance of 1D from the column face. We have two shear planes to be checked, 200 and 240 something. You see now your shear resistance of the peg footing is greater than the shear loads calculated. Therefore, your shear resistance is adequate. In the case that the provided shear resistance is inadequate, you will need to increase the thickness of the peg footing here. By increasing the thickness of the peg footing, you will increase the effective depth. Increase the effective depth. This leads to the increment of the shear resistance of the concrete and the shear resistance of the concrete minimum. By doing so, you will increase the VRDC, and then you're going to repeat the process until you get your VRDC greater than the VED. Let's say now you wish to go for a more economical solutions, or you feel that the thickness of the peg footing is too high, then you can choose to reduce the thickness and redo the calculations. Changing the thickness here, it shall result in changes in terms of the effective depth as well as changes in terms of the amount of reinforcement bar required. This may alter the AS provided and then influence the percentage of rebar and also influence the shear resistance of the section. You can do try and error until you come to the most economical design. This is about the shear resistance at 1D distance from the column face.